In this video, we're going to take a look at section 1.5, which is on compound inequalities. Before we take a look at the compound inequalities, we have a few concepts that we need to address. The first one are the set operations. The union of sets A and B is a new set that contains every element from set A and from set B. If there are any duplicates, if there's any elements that are the same in both A and B, we don't write them twice, we just write it one time in the new set. So we're creating a new set, and this new set gets its own label, which is this label right here. And so this symbol between the A and the B is called the union symbol. And it indicates that the two sets are being joined together. And everything from set A and set B are being thrown together into a new single set. The intersection of sets A and B, indicated by this symbol here, right? So we have A intersect B, that's how you would read this, and this is the intersection symbol, is a new set that contains only the elements that are common to both set A and set B. So this new set that we're creating contains only the things that the two sets share in common. In other words, it contains only the things that are duplicated in both sets. Anything that's unique just to set A does not go into the new set. Anything unique to set B does not go into the new set. It has to be common to both of them to be in the intersection of the two. These are very commonly represented by Venn diagrams. So for a union, so this is called the universal space here of just everything that's in the sets that we're considering, and usually you represent the individual sets as circles. So we'll have set A as this circle here, and we'll have set B as this circle here. The union of those two sets would be everything that's in A combined with everything that's in B. So the part here that I'm shading in, I don't know if I'll get to shade it in completely, but that would be the union of sets A and B. Contrast that with the intersection. Right, so set up the same situation. We have the universal space, and within that space we have set A, and we'll try to keep the same colors, and set B. The intersection of these two sets are only those things which the two sets share in common, which is only where they overlap each other. So just this part right here would be the intersection of sets A and B. All right, so that's how you can visualize the union and the intersection. So let's take a look at an example. So we have these two sets here. These curly braces are used to indicate a set of elements, and the elements that we're going to be looking at for the most part in this class would be numbers. And so we have in this set the elements of 7, 8, 9, 10, and 11. Those are the elements of that set. In this set here we have 4, 7, 9, and 16. This symbol, the right side up U, is the union symbol. So it's not really the letter U. If you look at it, you can tell it's not quite the alphabet letter U, but it does have the appearance of a U, and that's a good way to remember that that's the union. And that means we want to join, right? A union is joining things together. So we want to join these two sets together into a single set. So my answer, so what this is going to equal is one set, right? We're joining it into a single set with everything joined together. I'm going to combine it all together into a single set, and we'll try to keep it in numerical order. So of these two sets here, the lowest number, the one I want to start with, is the number 4. And so I'll put that first. And then the next highest number would be 7, which you'll notice occurs in both sets, but I'm not going to duplicate it in the new set. I'll just write it one time in the new set. And then we have 8, and we have 9, and then we have 10, and 11, and then 16 would be the largest number. So we just join these two sets together by putting all the elements from each individual set together into a single set. And this would be the union. All right. Now the intersection is indicated by the upside down U looking symbol. So this means we're looking for the intersection of these two sets, which means we want to create a new set, right? So this is going to simplify into a single set, but this new set that we're creating will contain only those things which are shared in common between the two sets. So for example, 0 will not go in this new set because 0 is not shared in common with both sets. 1 is not common to both sets, so we will not have 1 in the intersection. 3, however, is common to both sets, and so 3 should be in the new set, in the intersection of the two sets. 5 is not common to both. 6 is common to both, and so we'll put 6 here. 8 is not common to both. And so the only two numbers that exist in the intersection of these two sets are the numbers 3 and 6. Those are the only two that are shared in common. And so that is all that goes into the new set. And so this would be my final answer for this one. All right. Related to the union and the intersection are these logic operations, and or. And there's other logic operations like if, then, but in this class we're just going to be looking at and or. So to say, when you say the phrase A and B, that is only true if A is true and B is true at the same time. All right, so A and B is true, is considered a true statement as a whole, right? So we're looking at what's the truth of this statement in its entirety, A and B together. We consider that entire statement true if and only if the individual statements are both true at the same time. And so A would have to be a true statement, and B would also have to be a true statement for the entirety of that statement to be considered true. Or, on the other hand, is a little more laid back. So considering this statement in its entirety, A or B, that statement is considered true if either A is true, B is true, or if both are true. Then that entire statement is considered true. So we don't need both of them to be true at the same time, even though that would be okay. Or only needs one of them to be true for the statement as a whole to be considered true. And so, for example, if A is true, but B is false, the statement in its entirety would still be considered to be true because at least one of the parts was true. And that's all that or requires. As long as you're telling one thing that's true, the statement as a whole is considered true. All right. So let's consider some examples without, jumping into math quite yet. So let's look at some examples of and. The sky is blue, and 2 plus 2 is equal to 4. So I want to know if this statement as a whole in its entirety is true. For and, the only way that statement as a whole can be true is for the individual statements to be true. And in this case they are. The sky is blue, that's true. 2 plus 2 does equal 4, that's true. And so as a whole this statement is true. But let's look at these other examples. The sky is blue, that's true still. And 2 plus 2 is equal to 5. Well, that part's false. And even though part of this statement is true, for and to be considered a true statement, both parts have to be true. It's a very demanding word. Both sides of the and have to have true statements for the entirety of the statement to be considered true. And so because part of this is false, it ruins the whole thing. This statement as a whole, I'm going to circle the whole thing, and that's probably the last time I do that. This statement as a whole would be false because this part's false. And is not happy if even part of it is false. They have to both be true. And that's going to continue to be the case for the rest of these examples. The sky is green, that's false. So it doesn't even matter what's happening here. If part of it's false, then the and statement is false as a whole. The sky is green, and 2 plus 2 is equal 5. So they're both false. All right, so I guess let's go back to this third example. We have the sky is green, which is false. 2 plus 2 equals 4 is true, but again, if even part of it's false, the statement as a whole is going to be false. And if they're both false, of course, it's just a completely false statement all the way through. All right, so you can see it's pretty difficult to have and be considered a true statement. You have to meet both conditions. The first statement and the second statement have to both register as true for and to be considered true. Or, on the other hand, is much more flexible. The sky is blue, well, that's true. Or 2 plus 2 equals 4, well, that's true. They're both true. So for an or, the statement as a whole would be considered true. The sky is blue, that's true. Or 2 plus 2 is equal to 5. Well, that's false, but or, as we mentioned before, is pretty laid back. As long as part of it is true, the statement as a whole will register as true. And so, because we got part of it right, the first part, the sky is blue, that statement was true, or is happy with that, and as a whole will be considered a true statement, even though the 2 plus 2 equals 5 was false. And so I know it's difficult for students to accept that because they don't like seeing they don't like to see something untrue there, but for us to still say, well, this statement is okay, right? It's kind of like we're being lied to and we're accepting it, right? But or is like I said, it's a relaxed statement. As long as you're telling one truth, it's happy and will be considered true on the whole. The sky is green, that's false, but we can't make any judgments yet because we have to see what the other statement's doing. Here, we're saying 2 plus 2 is equal to 4, that's true. So or again will be happy, right? Because part of it was true, or is going to be considered as a true statement. This is the only way you can fail an or. The sky is green, that's false. 2 plus 2 equals 5, that's false. So if both statements are false, that's the only time or would be considered false. Right? So this is going to make or unhappy, and it's going to register as a false statement since both parts were false. Alright, so that's how and or work. These are very common words that are used in computer programming. For example, when you're logging into Math Excel, you give your username and your password, and the only way you're able to get into your account is if they're both correct. So when Math Excel in the computer code is checking your credentials as you're signing in, it's using an and statement because you have to have both the username, right? You have the username has to be correct and the password has to be correct. You have to get them both right in order to be allowed into the account. And so it has to check that both of these are true, that you got the right username and you got the right password. So it would be using an and statement in the computer code to make sure that you are authorized to access your account. If you get one of these wrong, if one of these comes back false, you don't get to sign into Math Excel. Or could be used, I'm trying to think what's a good example of when we might use or in computer programming. So for example, if you have a website and you want somebody, you want to direct somebody to a link or something, but maybe you have multiple ways to access it, you could encode this on your website where you would say, if they click on this text or if they click on this button, send them to this particular website, right? And so you're happy with whichever one gets clicked, right? As long as they're clicking one of those things, you want to go ahead and send them on to the particular website that you're linking them to. And so you might have something in your code that says, if they click on this particular text or if they click on this button, then perform this particular action. And in this case, it's an or, so it's looking out for either of these things registering as true. Maybe they click on the text but don't click on the button, and that's okay. You're going to go ahead and send them to that website. Or they click on the button but they don't click on the text. So again, the text would be considered false, but the button was true, so you go ahead and send them to the website. And the only time you don't send them to the website is if they don't click on either one, right? If these are both false, then you don't actually send them forward. So not the greatest example, but it kind of gives you an idea of how useful these words can be when you're doing computer programming. All right, we're going to be using and or with these inequalities, and we're going to be given two inequalities, and probably you would assume, given two inequalities, that you want both of them to be true at the same time, but that might not always be the case. It could be the case that you just need one of them to be true and not necessarily both of them. So we can't just assume, if we're given two inequalities, that we're trying to satisfy both of them at the same time. We have to look at the word that's connecting them together. So if the word that's given is and, right, if we're connecting these two inequalities with an and, then indeed that is the case. We want to find values of x that make both of these true at the same time. right? The sky has to be blue, and 2 plus 2 has to equal 4, right, for n to be happy. So we have to pick numbers that work in both of these statements at the same time. So for example, we could choose x equals 4, right? So there's other solutions that you could choose that work in both of them, but this is the one I just picked off the top of my head. So if we plug that in here, on the left-hand side we get 4 is less than 5. On the right-hand side we get 4 is greater than or equal to negative 2. So let's see if this will come out as true or false. Right. So 4 is less than 5, that's true. 4 is greater than or equal to negative 2, that's also true. So as a whole, the statement as a whole would be considered true, which makes for a solution not just to the individual inequalities, right, because it makes both of the individual ones true. It makes for a solution to the and statement as a whole, which is what we're ultimately looking for. We're looking for numbers that make the and statement true. Those are the solutions that we're trying to find. And 4 is going to be one of those solutions. So would 3, so would 0, so would negative 1. There's quite a few that you could have selected. What's an example of a number that would not be a solution to the statement as a whole? If you're having trouble thinking of one, it's because you're trying to find a number that makes both of them false at the same time, which you won't actually find. So any number you pick is going to work in at least one of these inequalities. It fails the and statement if it fails in just one of them. So I just need to find a number that doesn't work on both of them, right? 4 worked on both inequalities. Is there a number that maybe works on one but not the other? And you should be able to think of something. It may not be what I'm about to write down, but one possible suggestion you might have is the number 6. Right? So if I plug in 6 for x, what's going to happen? We'll have 6 is less than 5, and 6 is greater than or equal to negative 2. So is 6 less than 5? No, right? That is false. 6 is greater than negative 2. This is true. But as a whole, right, the and statement is going to register as false because and needs both of them to come out true in order to be considered true. And that didn't happen with the number 6. So 6 is not a solution to the and statement. It is a solution to this inequality, but it's not a solution to the statement as a whole, because on the whole it comes out false because it doesn't work in the first one. All right, so that's just giving you some background information. Sometimes I get students that are sort of annoyed with me because I like to, explain what's going on behind the scenes. And what a lot of students want to know is just tell me how to get the right answer on the homework. So here is how you will find the solution set to these and compound inequalities. This is the way I would recommend doing it. I would suggest graphing both of these individual inequalities, this one here and this one here, on the same real number line. So I'm going to draw one real number line. I always like to put 0. We have positive 5, which will be to the right of 0. We have negative 2, which will be to the left of 0. And graph both of these on the same real number line. So I'm going to graph this one in red. So here's 5. Less than 5 would be to the left of 5, so it's going to go this way. And then because there's no equals to there, we will use a parentheses. Right, so we learned that in the previous section in 1.4. This inequality we'll do in blue. So negative 2, we want numbers that are greater than negative 2. That'll be to the right. That's where the numbers get bigger as we go to the right. Because there is an equals to here, we want a bracket. Now, I ran into a little bit of trouble here because my first graph got in the way of my second graph. So the way I handle that is I like to do one graph just above or below the other one. I see students on their homework and on their test, they'll just kind of have them on the same level where they kind of crash into each other. That's fine. What you're looking for is you're looking for numbers that make both of these true at the same time. Meaning you're looking for numbers for the and statement that are on both the red graph and the blue graph simultaneously. Those are the numbers that work in both inequalities at the same time. For example, 4, right? 4 is on the red graph and it's also on the blue graph. So it makes both inequalities true. That's what and is looking for. So what you want to look for when you put this graph together are where are the graphs overlapping each other, because where they overlap are where we will find the numbers that make both inequalities true at the same time. So the word I always like to associate with and is overlap. Find where the graphs overlap each other and you'll find the solutions to the and compound statement, the inequality as a whole. So wherever they're overlapping, which is right here from -2 up to +5. So I'm going to redraw my graph, shading in just where they're overlapping. So from -2 up to 5. Brackets on the -2, just like we have in the graph up here, and parentheses on the 5. All right, so this would be the graph for my solution set. To write this in interval form, which we are being asked to do, you can see that up here in the directions, you go from smallest to largest, and again, referring back to section 1.4, whenever we were writing intervals, an infinity would show up in one way or another. So it'd either be positive infinity or negative infinity. This answer does not have an infinity, right? The smallest number in the set is -2. The largest number in the set is +5. And so it's just going to go from -2 to +5. And that'd be my interval. Brackets on the -2, parentheses on the 5. So that is graphing and writing the solution set to this compound inequality in interval notation. And that's how AND works. Fortunately, OR has a little bit of a different behavior. So we want to graph this compound inequality and write this solution set in interval notation. Now for OR, we are happy as long as we get one of them right. We don't have to find numbers that work in both. So when I ask students in class, give me a solution to this statement, they struggle because what they're trying to think of is, well, I want a number less than -4 because that's this first inequality here. But I'm also looking for a number that's bigger than 5 because that's the second inequality. So let me see if I can think of a number that's less than -4 or bigger than 5. You can't. That's impossible. There's no such thing as a number that's smaller than -4 but bigger than the number 5. But you don't have to find a number that has both of those descriptions because OR doesn't need that, right? OR is not asking for both of these to be true at the same time. It's just saying, give me a number that satisfies at least one of these conditions. I need numbers that are either less than -4 or bigger than 5. I'm happy with either kind, right? So a solution to this inequality would be something like -5. Right? So let's plug that into this this compound inequality here. So -5, we'll plug that in for x, so we get -5 is less than -4, or -5 is greater than 5. So let's see if this works here. Is -5 less than -4? Yes, that is true. Is -5 greater than 5? No, it's not. That's false. But for an OR, all we had to do was get one of these right, and OR is happy, and will register as true for the statement as a whole. And so this OR statement will register as true because we got one of the things correct. And so -5 is a solution to this compound inequality. As long as you're getting one of the criteria right, it's a solution to the compound inequality when it's an OR. Another example of a solution would be x is equal to 7, right? So if we plug in 7 here, we'll have 7 is less than -4, or 7 is greater than 5. Is 7 less than -4? No, that is false. But is 7 greater than 5? Yes, that's true. And for an OR, as long as one of these comes out true, we're happy with it. The statement as a whole registers as true. It's actually more difficult here to find a number that doesn't work, right? So maybe it's not too hard to find, but there's a lot more numbers that are solutions here than are not solutions. Something that doesn't work, however, would be like 0, right? So 0 doesn't work here. So if I plug in 0 for x, we get 0 is less than -4, or 0 is greater than 5. And the reason OR isn't happy with 0 is because it doesn't make anything true. Right? 0 is not less than -4. That's false. 0 is not greater than 5. That's also false. And so that's the only time OR is unhappy, is if both statements come out false. So 0 doesn't work. All right. So that's kind of how an OR works. But again, just like the last example, you're probably thinking, okay, I didn't need all this detail. Just tell me how to do the problem on the homework. So I approach it in the same way. I graph both of these on the same real number line. So I'm going to graph this first inequality in green, and I'll graph the second one in blue, let's say. So let me set up a real number line, graph both of these on the same real number line. So I always like to have 0. We have -4, which is to the left of 0, +5, which is to the right of 0. And for less than -4, that would be to the left, right? If we want numbers, and that sounds kind of funny to say to the left, right? Apologize for that, but it's to the left, correct? Because numbers get smaller to the left, so I want the numbers that are smaller than -4, which would be to the left of -4. Forever to the left, it'll just keep going. Parentheses on the -4 because there's no equals to. Greater than 5 would be all the numbers to the right of 5. That's the direction in which numbers get bigger, is going to the right. And if we want numbers that are bigger than 5, those would all be to the right of 5. Again, parentheses on the 5 because there's no equals to. Now they don't overlap each other, but OR doesn't need them to overlap. Right? If this was an AND, we'd be in trouble, right? Because for AND, we have to have them both true at the same time. That only happens where they overlap, and if they don't overlap, then it's never true. Right? But for an OR, it's fine. They don't need to overlap. What you want to do is keep everything. The word I like to use originally was combine. You want to combine these shaded regions together. So for an OR, you combine. But I had a student who told me at one point the way they like to think of it was keep everything. So when you're working with OR, you shade in both inequalities on the same real number line and keep anything that gets shaded in. You just keep all of it, right? So keep everything, if you like to think of it that way. I like to think of it as combined together, right? Because it's a union, it's joining. We're actually referring back to the first topic we talked about. We are joining these two solution sets together into a single solution set. So this is it. This is my answer. So I don't have to just take where they overlap. So notice in the previous problem, we wanted only where they overlap, and we ignored everything else, right? We cut off the rest of this red line and the rest of this blue line and just kept where the two were overlapping. That does not happen with OR. You don't leave anything out. Nothing gets excluded. You keep everything when you're dealing with OR. And so I'm keeping all of these numbers. I'm keeping all these numbers. So this is my graph. To write this in interval notation, it's a little bit tricky because there are two separate regions, and each one has to be written as its own interval. So this region here, the interval for this would go from the very left, which is -infinity, to the very right, which is -4. Always put parentheses on infinity, and this -4 has a parentheses, as we see here in the graph. This graph translates to the interval 5, right, from the very left, which is 5, to the very right, which is +infinity. Parentheses on the infinity, and then as we see in the graph here, we also have parentheses on the 5. And so we get these two separate intervals that we want to join together. We want to combine the two together, so we use the union symbol. And so this would be my final answer, joining those two intervals together. So that's where the union comes in. So OR is associated with the union symbol. AND is not. So if you have an AND compound inequality, you should never be using the union symbol to represent the answer for an AND. It doesn't go with AND, it only goes with OR. What does go with AND is the intersection, right? But you should never use the intersection symbol either on these problems, because that can always be simplified, right? So if you rewrote this AND as an intersection, this inequality here goes from -infinity up to 5, and we want to intersect that with, sorry, it should be a bracket, -2 to infinity. So this would be another way of writing the answer, and becomes an intersection. This inequality gives you this solution set, this interval here. This inequality gives you this interval here. And then you want to intersect those, which means you want to find what these two share in common. Where do they overlap? Which simplifies down to this. So the problem with the intersection symbol is that it can always be simplified to something without the intersection symbol. So you shouldn't use it. For an AND, we won't use the intersection symbol, even though that's the appropriate symbol for that word, because intersections can always be simplified down to a single interval, at least with the material that we're working with. But OR can't always be simplified down to a single interval, as we see here. We get these two separate intervals that cannot be simplified any further, so we actually are stuck using the union symbol here. We have to use it in this situation. All right, so the problems in general are going to look more like what you see on the screen now. And while this looks like it might be a lot more complicated than what we were just doing, the hard part is what we were just talking about. Getting to that part is pretty easy. What you want to do with these is you want to solve both of these as if they were equations, right? We're going to solve both of these inequalities for x the same way you would solve equations for x. Once you've solved each of these for x, the problem goes right back to looking like these two that we just did here. All right, so once I solve for x, I'm going to get something that looks like this, which I will then find the solution set for in the same way that we did here, using the same process. So every problem in this section will boil down to something that either looks like this with the and, or something that looks like this with the or. So every problem becomes something like what you see here. All right, so let's go ahead and get it into that form. So we're going to solve this one for x the same way we would solve an equation. We're going to first subtract the 4 from both sides, and we'll get negative 12 is less than or equal to 4x, and then we will divide by 4 to get x by itself. So like I said, not too much work. And we didn't divide by a negative, so I don't flip the symbol around the other way. I divided by positive 4, so the symbol stays the way it is. Negative 12 divided by 4 will be negative 3. So that's solving that one for x. We'll do this one, same thing. We will subtract 4, and this one they happen to be the same expression, so it's going to be the same steps. Subtract 4 from both sides. We get 4x is less than 24, and then we will divide by 4, and we'll get x is less than 6. The and will still be here between the two inequalities. That's not going to change or do anything different. So this is what we get when we solve for x. Now, this is sufficient, and you could type this into Math Excel and find the graph and the interval based on what we've done so far. But in fact, you may have to leave it like this, because I think what they want us to do on Math Excel is write these as a single inequality. It's still a compound inequality, but write it as a single expression instead of two separate expressions. And the way you do that is you overlap these x's together, right? And you can only do this with and. Let me try that again. So this, what we're about to do, does not work if this is an or. So we can overlap these x's on top of one another so that we can just write the x one time instead of twice. And then to the left we'll have this expression here, which is the less than or equal to symbol and the negative 3. And to the right we're going to have the less than symbol and 6. All right. And then that's what you're going to want to type into Math Excel. They will have this part already set up, and then they'll have boxes for you to type in the numbers, but you'll have to pick the right symbols. They'll give you different options with the symbols going in different directions. So make sure you pick less than or equal to for the first one and less than for the second one. Make sure you choose that option on Math Excel. And what we're going to do is to find the solution set as a graph and to write it as an interval is we'll graph both of these on the same real number line. So we have 0, we have negative 3, and we have positive 6. Now the tricky thing about graphing both of these on the same real number line is when x is on the right hand side, it's very common for students to shade in the wrong direction. Because they see this is a less than, they think I'm going to shade to the left, because less than means the numbers have to be smaller and smaller is to the left. But it's backwards, right? It's not that x has to be smaller than negative 3, it's the other way around. Negative 3 needs to be smaller than whatever we pick for x, which means x needs to be bigger than negative 3. So we actually want to shade to the right. And if that was confusing, let's just avoid that confusion by taking my advice, which is to always have x on the left-hand side instead of the right-hand side. So you can flip this around, put x on the left-hand side, put negative 3 on the right-hand side, just like you would flip an equation around. But the thing about inequalities is when you flip an inequality around, the symbol has to flip around with it. So this less than gets flipped around and becomes a greater than. And so I would rewrite this like this, And that way you're making sure you're going to shade in the right direction. So we need to shade to the right of -3 for greater than. So all the way to the right, brackets on the -3. For the other inequality, we have x is less than 6. Less than is going to be to the left, right? That's where the numbers get smaller. And so we're going to shade to the left. Parentheses on the 6 because there's no equals to there. And because this is an and, we want to find where these are overlapping each other, which is between -3 and +6. So my final graph is going to look like this. So brackets on the -3, parentheses on the 6. All right, it's a pretty bad parentheses. And then as an interval, we go from the very left to the very right. So that's going to go from -3 to +6. Brackets on the -3, parentheses on the 6. And that would be the answer in interval form. If you even have to type that in. I don't see it asking about that up here, but I just like to put that as part of my answer because I mentioned in the last video, when you're doing inequalities, graphing and intervals I think are both good to do for every problem. Okay, what if it's an or? You approach it in the same way. We're going to solve both of these for x. So I'll start with this one. We'll subtract 6 from both sides to get things started. So we'll get 1, which is showing me right away that we're going to be dealing with a fraction here. To solve for x, we will divide by -4 on both sides. So on this side, we'll get -1/4. On the right-hand side, we're going to get x. And I kind of mentioned it already earlier in the video, so hopefully that reminded you, but something we haven't seen yet in this video is when you divide by a negative on both sides, you have to flip the symbol around the other way. So that's still in effect. So we divided by a negative on both sides, so this less than gets flipped around and becomes a greater than. And like I said, for graphing this, it's kind of hard to do when x is on the right-hand side, so I like to flip it around, have x on the left-hand side, -1/4 on the right-hand side. When I flip this around, the symbol will flip around with it. All right, we're going to do the same thing with this one. We will subtract 3 from both sides, and we will get 5 is less than or equal to -2x. Same thing's going to happen here. We divide by -2 on both sides, so I'll get -5/2, right? Positive divided by negative makes that a negative. The fraction doesn't reduce, so we just leave it like it is, like 5/2. But because I divided by a negative on both sides, I got to flip the symbol around the other way. And then, because x is on the right-hand side, makes it kind of hard to figure out which way to graph, I'm going to flip this around, put x on the left-hand side, -5/2 on the right-hand side. The symbol has to get flipped around with it, and so we get this. It's still an or, so I'm going to put or down here. And so this is solving the inequality for x. So you should have an option on Math Excel that has an or. We cannot use the option we used in the last example where we overlay the x's and write it as a single expression. That does not apply for ors. So we have to find an option that specifically says or, and then with the inequality symbols facing in the right direction. They might have it in the opposite order, so they might have the less than or equal to first and the greater than second, so be careful the order you type the numbers in on Math Excel. Once we have these both solved for x, we can find the solution set by graphing both of them on the same real number line. So we have, I like to put 0. I'm going to put it a little bit to the right this time because both of these numbers are negative. So they're both going to be on the left-hand side of 0. So I just want a little more space to work with over here. And we do want to get these in numerical order. So as a fraction, if you have trouble figuring out which one's bigger and which one's smaller, you might want to use your calculator, see what these are as decimals. This is 0.25, so -0.25, which is going to be pretty close to 0. So it's going to be right close here. And then this is -2.5. It's pretty big, right? 2.5 is going to be quite a bit further away from 0, so it's going to be further to the left. So -5/2, let's say, is right there. All right, so we want to shade to the right of -1/4 because we want greater than -1/4, which will be this way. Parentheses on that because there's no equals to. And less than -5/2 means we want to shade to the left of -5/2. Brackets on that number because of the equals to in that inequality. And for an or, as we mentioned earlier, we keep everything. And so everything I just shaded in stays shaded in. And so that's my answer. This is what my graph should look like. As an interval, it's going to go, we have two separate regions. The first region is going to go from negative infinity up to negative 5/2, and that's where it stops. And then the solution set doesn't resume again until negative 1/4. So the second region starts at negative 1/4 and then goes forever to the right, so it's going to go to infinity. So again, going from left to right. And because I had to write that as two separate intervals, I want to show I'm joining those together as a single solution set, so we use the union symbol to indicate that. All right, and so that is typically how an OR works out. You can have wonky cases where, for example, the AND doesn't overlap, in which case there's no solution. You can have OR cases where they cross each other, in which case everything gets shaded in, and if you keep everything, you get all real numbers as your solution. So you can have some unusual outcomes. You can also have outcomes that look like this. I don't know if I have an example that, I think I have maybe one more example to do. We'll see if this ends up being one of these cases. But you can have examples that kind of go like this, where they both go in the same direction. And so you have to be kind of careful how you interpret your answer when both solutions are going in the same direction. If it's an AND, you want where they overlap. If it's an OR, you just keep everything that gets shaded in. So you still follow the same rules, but the answer works out in a way that's a little bit atypical. All right, so let's see if we have such a case here. Looks like I have maybe one more example. Yeah, okay. So I got two more, this one and one more. So we'll do the same thing we did on the last one. All right, we're going to solve both of these for x. So I'll start by subtracting 18 to the other side. We'll get 3x is greater than or equal to negative 3. And then we'll divide by 3 on both sides. And so we're going to get x is less than, or sorry, I said the wrong word. X is greater than or equal to, let me write that again. I kind of feel like I didn't do that in the best way. Negative 1. Okay, let's go ahead and solve this other inequality for x. So we will start by adding 21 to both sides of the inequality. That'll leave us with 3x is greater than or equal to 3. And then we will divide by 3 on both sides. And we will get x is greater than or equal to 1. And in between the two inequalities, we still have and. So this is solving it for x. Now this one's going to be one of our unusual cases I was alluding to just a few moments ago, because these are both going in the same direction. So we're going to have to be a little careful here. This answer is not going to work out in the normal way that we have been seeing so far. And so we'll follow the same procedure though. If you follow the same procedure, you'll get the right answer every time. We'll graph both of these on the same real number line. We have negative 1 and we have positive 1. All right. And I guess let's stick with the same colors. So we'll graph this one in blue. Starting from negative 1, we want the numbers that are greater than negative 1, which will be to the right of negative 1. And then brackets on the negative 1 because of the equals 2. And then for the second inequality, we want the numbers that are greater than positive 1, which will be to the right of positive 1. So they're both going in the same direction. For AND, we're looking for numbers that satisfy both inequalities at the same time, which will be where the two graphs overlap each other, which will be right here. All right, so this area right here are the numbers that are solutions to this compound inequality. So only from positive 1 to infinity. So even though I like to still copy down the same numbers here for the redrawing of this graph, I'm only going to be shading in the numbers from 1 to infinity because that is where the overlap is occurring. So I'm only going to shade in this region right here. And that's going to be my final answer. As an interval, this goes from positive 1 to infinity. All right. Last example. So this one is set up in an unusual way. I guess it's not unusual, but a way that we haven't seen yet anyways. So this is also a compound inequality. We have two inequalities here. We have negative 14 is less than or equal to negative 2x minus 9. We also have that negative 2x minus 9 is supposed to be less than 0. And while it's not explicitly stated here, anytime an inequality is set up in this fashion, it's always an AND. You can never set an OR up in this way. So this is automatically an AND compound inequality. So we want both of these inequalities to be true at the same time. Right? We want negative 14 to be less than or equal to negative 2x minus 9 and negative 2x minus 9 to be less than 0. And I used to teach this by telling students rewrite it as a compound inequality by writing it as two separate inequalities, put AND in the middle, solve each one for x. And that is a more tedious way to do the problem. And when students found there was a easier method, I found I kind of lost their trust a little bit. Like they didn't trust me to tell them the best way to do the problem. So I stopped doing that, and I'm gonna, so that I can maintain your trust, I'm giving you what I think, in my opinion, is the best way to do these problems that gets you the right answer every time. So I'm not giving you shortcuts that work 75% of the time. I can't do that, right? As the teacher, I have to give you methods that work 100% of the time. So this is the easiest way to do this problem so that you always get the right answer. And that is to solve for x in the middle. So we want to get x by itself here in the middle. And so we're going to get rid of all the stuff that's around x the same way we would do for solving an equation. So for example, to cancel out the minus 9, I'm going to add 9. The thing is, there isn't just both sides to worry about, there are three sides to worry about. There's the left-hand side, the right-hand side, and the middle. So whatever you do to the middle to get x by itself, you have to do to both outsides, the left-hand side and the right-hand side. So if I'm going to add 9 to the middle, I have to add 9 to the left-hand side and to the right-hand side. So on the left-hand side, we'll get negative 14 plus 9, which will be negative 5, less than or equal to negative 2x will be left in the middle, less than 0 plus 9, which is going to be 9. Then, to get x by itself, we'll divide by negative 2 to cancel out that negative 2. If I do that to the middle, I have to do that to both the left-hand side and the right-hand side. And because I'm dividing by negative on both sides of this inequality, I have to follow that rule, which is flip the symbol around. Here, the double negatives cancel out, so we get positive 5 over positive 2, so 5 halves. In the middle, the negative 2's cancel out, so we just get x. And again, here we divide it by a negative on both sides, so flip this symbol around also, and we'll get 9 over negative 2, which is negative 9 halves. All right, so that's solving it for x. This is what we get. And then when I go to over here to type in my answer, notice that they have it set up in this kind of weird way. The solution set is any x such that blank is true. We want to type our numbers into these two boxes, but don't just assume, okay, I just type it in the order that I see them here. We have to pick the right one first. And we have our symbols going the wrong direction relative to what MathExcel was wanting. So if this was an exam and I'm grading it on paper, I'd be perfectly happy if you left it like this. There's no reason to change it. This is fine. But to get it to fit into MathExcel, we want to flip this around. So what you're going to do is flip the whole inequality around. I'm going to put the negative 9 halves on the left-hand side, the positive 5 halves on the right-hand side. When you flip it around, x will still be in the middle, but just like we did earlier when we were flipping inequalities around, if I flip the whole thing around, the symbols have to get flipped around with it. And so this symbol flips around over here and goes the other direction, so it's going to go this way. And this symbol is going to flip around here and again go the other direction. So it's going to look like this. So the symbols trade places and they flip around the other way. So just imagine, you know, a line right here and you're rotating it 180 degrees, right? So we're spinning it around this line. These symbols are going to get flipped around the other way, right? And so this is another way of writing the same answer, and this fits more with what MathExcel is wanting to see. So it looks like C is the correct choice, and we'll type the numbers in here, negative 9 halves, which is less than x, which is less than or equal to positive 5 halves. Sorry this video went a little bit long. I have one more thing I thought of as I started this problem, which is for this, they may want the same thing. They might want you to write your final answer as an interval, which you wouldn't want to leave like this. If you look at your final answer, the solutions are just numbers that are bigger than 1. So the final inequality would be any number x that is greater than or equal to 1. And so this simplifies down to this inequality here. So when you look at the graph, you can So my advice would be to simplify this compound inequality. In the cases where that's possible, you can do that by looking at the graph that you have and basing the inequality off the graph, right? So my final answer in the graph is numbers that are bigger than 1. That's the final way I want to write my inequality. Again, just real quick, we're almost done. I don't think it's asking for this here, but I like to do this on every problem. So the graph here is going to go from -9/2 to +5/2, right? And so we're going to go, so those are the two numbers in my answer, and we want x to be between those two. Parentheses on the -9/2, brackets on the 5/2. And so we'll shade in between those two numbers. So as an interval, that's going to go from -9/2, comma, to +5/2. Parentheses on the -9/2, brackets on the 5/2. Even if it doesn't ask you for that on the homework, being able to write intervals is going to be something that will be helpful later on in the course. So, so that's section 1.5.